All right. So I'll be talking to you about HPCQC integration system workflows that we've been working on here at LRC. I'm one of the researchers in the quantum integration software team at the Leibniz Supercomputing Center. So we have the general problem of the way that quantum computing is approached, at least on a basic level, and what it used to be was the kind of standalone workflow where we have an entire problem fits into a quantum problem or a circuit or program. And you can see that kind of illustrated over here. We have a classical host. Some kind of work is done there in terms of orchestration, and we basically click a button and that gets sent to the quantum computer, and that's actually doing computation. This doesn't really necessitate any interaction on the classical compute resources that we have in supercomputing centers. And the optimization is also usually done only once, of course, when the quantum computer scientist is developing their software. And it's really, at least in the current NISQ era, it's used to enable computability much more than actually caring about the time. So it's much more focused on the fidelity and the error that is produced in a quantum program. Now, with hybrid workflows, which is, well, there's two different things. There is iterative, and variational is a subset of iterative. And there's the separable algorithms, which are effectively quantum tasks that are spawned from a classical superset program that, for example, is a Shor's algorithm execution, where each individual quantum task is independent of each other. You see those illustrated over here. But the main characteristic is that these things iterate in terms of the iterative class. And on the separable class, it's that there are many different quantum tasks that are only solving a partial set of problems. So this makes QPUs accelerators. Of course, we can argue about what's accelerating what at this point. Not having a single execution of a quantum program, though, causes issues because there is now orchestration inside your compute-only program. So if we could compute something on the classical side where we don't need to worry about orchestrating anything, that would be great. If we could have a quantum-only program, that'd be great too. But now we have to deal with this kind of consistent and more or less permanent exchange of data between these two domains. So that's kind of where we come in. We're looking at exactly that. How do we deal with this shared contended for resources? So what we usually have is, of course, GPUs in our supercomputers, where GPUs are allocated to a job and they are not shared. They're, of course, maybe shared on a single node, but they are not shared across jobs, and jobs don't really interact with each other. However, we are going to be moving past that boundary with the quantum accelerators that we get. That is, for one, because these things are really quite large compared to a small GPU. And they're expensive, and there's not that many of them. They have control electronics, cryostats, depending on which technology we're talking about, and a whole bunch of other things that make them not possible to be easily miniaturized and not possible to be easily kind of segmented away from a system. And of course, for us, from a center perspective, we care about the efficiency. So as we do on classical applications, interact with other programs and other jobs over a network, so contention. However, we don't contend for a GPU usually. With a quantum computer, this is a much more explicit contention, and we have to kind of figure out a way of dealing with this. Aside from just scheduling access, it's also kind of important, what do we do on the classical side to orchestrate this access? Who does the optimization? Where do we do that optimization? And how do we choose which task goes to which quantum computer, which is, of course, the scheduling problem. So we actually published a paper about this 2 weeks ago at SC in one of the workshops, quantum software, computing software workshop. It effectively tries to answer some relatively basic questions that you get when we have a kind of an integrated setup that requires us to determine what do we want to do when. So the question, my initial question to our researchers was, if we knew a circuit was not optimizable, would we want to run an optimization? And of course, the answer is no, because you don't want to spend classical time, even if it's trivial compared to the quantum time that is spent in terms of cost. You still don't want to waste that time. And you also don't want to delay anything anywhere for no reason at all. So we went about and kind of used a model, an LSTM, to predict whether a circuit is optimizable at all. And we actually got a relatively accurate number out of it. 96%, I believe, was the answer. And really, the intention was to figure out whether something is optimizable, not only for the sake of optimizability, but really, how does this, to figure out how this fits into the bigger picture of the general trade-off between how much does it take to execute a quantum circuit. That means the reprogramming time, the number of shots that they do, of course, the amount of time that it takes to optimize a circuit, which is non-trivial, the kind of all the offload mechanisms that have to jump into place in terms of sending this over a network or over the internet to somewhere, what is worth it to do when, and having information for these decisions. Over here, you can see our plot of kind of our main results. It's basically saying that as you increase in depth, our relative error goes up, unsurprisingly. Multi-qubit gates also increase our error much more than single qubit gates. However, we can somewhat predict this. So this all fits into the bigger topic, which is our decision pipeline or decision workflow. So when we get a circuit submitted by a user, an arbitrary user on our systems, and it doesn't matter what they're doing, we have to choose a target device that we want to send this to, assuming there is not a exclusively allocated one for a job of a user. We have to translate it down to that basis gate set and all that, which is a polynomial process, so it's not horrible. But then the question becomes, well, do we want to optimize it, or do we want to just send this off to execute the circuit as soon as possible so we get the result back to our user? And that's kind of the tricky part, because if you have a circuit that is, maybe optimizable by 2%, it may not be worth spending 20 minutes trying to find that optimal transform that matches the equivalent or equates the one that they initially gave you. So we just want to go and execute it as soon as possible. Whereas if we know that an optimization can be done and it can be done in a small time window, then we might want to do that and optimize our usage of the system. Because again, as a center, we are particularly interested in increasing our throughput of tasks, not necessarily our users' latency, let's say.